Hi, everyone, and welcome to our poster presentation here at the European Space Weather Week. So our research focuses on using ML to characterize magnetic reconnection in the 3D regime and to better understand the spatiotemporal evolution of the structure of the magnetic field using high-fidelity supercomputer-generated plasma simulations. So first, we begin our analysis by extracting some meaningful topological features from the 3D magnetic field, namely magnetic nulls and separator curves. Magnetic nulls are points where the magnetic field essentially vanishes, and they can be classified into 4 different types that characterize the local topology of the field around them. And these magnetic nulls can be connected via separator curves that form at the intersection of the fan surfaces of the 2 connected nulls. So in previous work, we extended the traditional definition of null graphs to spatiotemporal null graphs, which encode the separator connectivity via special edges. And in addition, they help with null point identifiability by tracing the temporal evolution of each null point and encoding them using temporal edges. By the way, if you're interested in reading more about our previous work on spatiotemporal null graphs, you can find a previous article right here, or contact us if you'd like to get in touch. So over time, what happens is that null points can switch types, appear or disappear due to physical phenomena such as bifurcations. And what we did is we used the previously developed spatiotemporal null graphs to detect appearing or disappearing null points, and then use this information to construct labels that we can then use with different learning setting formulations. So we have 3 learning settings that we explored in this work. One multi-target regression task, where we forecast the total number of null points of each type for each grid cell, and 2 multi-label classification settings, under which we forecast whether a null of a specific type appears or disappears, again within each grid cell. So what we've come up with is an architecture prototype to help us work with large-scale plasma simulations and get some useful insights on the appearing and disappearing null points throughout the temporal evolution of the field. So this architecture prototype can be adjusted with only a few minor modifications to work with any of the learning settings that I just mentioned. So this architecture consists of 2 modules that are optimized jointly. The first module is a downsampler that essentially learns a non-uniform downsampling of the input. And in this module, we use an attention map that works such that for each cell in the input grid, if the cell contains a null point, it will be assigned a higher weight in the attention map. And from the element-wise multiplication between the input and the attention map, the covariates that are associated with cells that contain nulls are highlighted, and the impact of their information remains then less diluted throughout the special convolutions of the downsampler. So then the output of the downsampler is compiled into sequences and used as input to the temporal convolution module, the second module. So the temporal convolution module comprises of a sequence of 4D convolution layers, and they're 4D because they're simply like 3 spatial dimensions plus the temporal dimension of the sequence. And finally, through a fully connected layer, the input is mapped to the predicted output vectors. So this is our architecture. And in closing, some open questions that are stepping stones to our future work are, for instance, could we use this work for speeding up the plasma simulator we have been using? Or how can we make the modeling process of such phenomena more interpretable so that we can also gain some physical insight on their inner workings? And finally, how can we extend this work to learn the spatiotemporal evolution of separators too? Thank you so much for taking interest in our work, and please reach out to us. You can contact us at this email to plan a meeting during Space Weather Week, and let's continue the discussion. Thank you so much.